Hello, Professor. This project focuses on detecting fraudulent credit card transaction using machine learning. Fraud detection is difficult because fraud cases are rare, but the cost of missing them is very high. Our work emphasizes on how data preparation choices influence model reliability and fairness. I'll first introduce the problem and dataset, then walk through data profiling, cleaning, and EDA. After that, I'll explain on how we handle class imbalance, followed by our modeling approach, results, and feature interpretation. We'll end with a short reflection on what we learned as well. In fraud detection, we are searching for a rare abnormal transaction within extremely large datasets. Two challenges arise: severe class imbalance and noisy raw data. To address this, we prioritize improving the dataset before model training. So, this allowed us to better evaluate whether performance gains were coming from cleaner data rather than model complexity. Specifically, we removed duplicate scale features, applied mode to address class imbalance, and then trained random forest and neural network models. Our goal was to demonstrate that improving data quality leads to better performance and fairer outcomes on the set. The dataset contains European credit card transaction with anonymous features for privacy. It includes over 280,000 records and 31 variables where most features are PCA transformed components. Profiling showed no missing values, but we identified duplicate transactions which were removed to prevent bias and leakage. This step helps us understand the structures and limitations of the data before analysis. Now I'll pass my slides to Qingjin.
Question is introduction, then it comes to data cleaning and EDA part. Well, after data profiling, we found that there are 1081 duplicate rows, so we removed them before any modeling. And we did not drop any rows for missing values because there were no missing values. So this step was purely duplicate removal. And then it comes to EDA parts, we first focused on the class distribution. We plotted the distribution of the target class after removing duplicate. We found that the non-fraud dataset accounts for 99.83%, and the fraud data only accounts for 0.17%. So the imbalance problem is significant. Well, a model that always predicts non-fraud would get 99.8% accuracy but zero fraud detection. So accuracy alone is misleading. We therefore focused on recall and precision together and used the F1 score and the ROC-AOC curve as well to measure the performance of the model. So this imbalance motivated our use of SMOT on the training set. So the model could learn from patterns instead of ignoring the minority class. And then we use EDA to find the transaction patterns of the dataset. Well, as for the amount by class, we compared transaction amount between fraud and non-fraud. Fraud had higher mean amount and higher variance than non-fraud, so this suggests amount is a useful signal. Well, for the time, we looked at transaction time patterns. The dataset uses seconds elapsed since the first transaction. We used these as a feature after scaling. Well, we also built correlation heat map between features and the target. Several PCA-derived components, such as components 14 and 17, showed a noticeable correlation with class, confirming that the norms features carry a predictive signal for fraud. Together, these 80 steps justified keeping amount, time, and the 28 PCA components as inputs for the models. Then we would like to prepare for the data. First, we scale the data. Well, since the 28 PCA-derived features were already on a comparable scale, we applied the standard scaler only to time and amount. Well, also we split the cleaned data, 80% for training, 20% for testing, and the test set was not used for smooth tuning or training, and it is only used for final evaluation. Well, why to do this? Because duplicate removal and scaling were done on the full dataset before the split. Smooth was applied only on the training set, so the test set stays representative of real-world class imbalance. And I would like to hand over my slide to the next person. Thank you.
So moving on, we had very less fraud data, as mentioned before in our project. And so we had to use Smote to sort of generate some fraud data. And as you can see, we had less than 1% of fraud in our raw data. And so it was just, if we had to use some models, it would just ignore the minority class. And so we used Smote to sort of generate new synthetic samples that we had also learned in class. And so we can see on the side the two charts of the class distribution before Smote and after Smote, and we sort of did it only on the training set. And so for the training set, we got a 50-50 distribution. We left the test set unchanged, right, which was still imbalanced, so that we could sort of evaluate it on the real world performance. Um, Talking about the models that we use now, we use two models. We used a random forest and a neural network. For the random forest, we first trained it on a baseline without any, with just the default hyperparameters, and then we tuned it also. So we'll show you the results for both of them. And for neural network, we used a feed-forward neural network with the common dense layers and dropout. Um, so we use random forest because it's very it's good for performance and it's very explainable compared to a neural network, and it also can handle the nonlinear patterns, and we can also tell you about the feature importances which we have taken up in the later slides. So that was for the base model, and then we tuned it using a library called randomized search CV, right? And then we sort of chose the best model according to this ROC AUC metric, just seeing the area under the curve, which we'll also show you in the coming slide. And so all our models were again held out on the test set, which was just, as we mentioned, 80-20 split. So 20% we measured it on the basis of the accuracy, precision, recall, F1 score, and ROC UEC. Um, Talking about now the results that we got from the random forest, right, as well. This is a baseline version without tuning, basically. We basically saw that this was again on the Smote balance training set, of course. We use that for all our models, which after Smote we performed the model training. So we achieved a very high accuracy, which was 97%. But in this case, right, it was very we got some very low precision because it regarded many like legitimate transactions as fraud, which basically implies very high false positives. So it did catch a lot of fraud, as we can see on the chart, right? 56,635. But it was also at the cost of many false alarms that we can see. And so this is not very suitable for deployment because we need a better separation between the fraud and the non-fraud. And so on the next slide, which is this one, which is where we tuned it, right? And we tuned it using this randomized search CV. We evaluated it again on the test set, and we achieved a better accuracy as well as a better precision. So we achieved a 99% accuracy and a precision of about 81%. And so so this model basically correctly classifies all the transactions, and 81% of those alerts are also true fraud, and 76% of them are actual frauds. So we have less false positives in this case. And so as we can see, this conclusion that we have drawn over the random forest untuned versus tuned is that we get a better balance between catching fraud and right. And basically we chose the random forest as our main model with the tuned version, of course, with this randomized search CV. Um,
Now, I will briefly discuss feature importance and our final reflections. Using the tuned random forest, we extracted the feature importance to understand which variables contributed the most to fraud detection. We visualized the top 15 features and found that the most influential predictors were primarily PCA-derived components, especially V14, V10, V12, and V17. Although these components are anonymized and cannot be directly interpreted, their importance indicates that lantern transaction patterns captured by PCA are highly predictive of fraud. From a business perspective, feature importance improves model transparency and help analysis focus on high-risk transaction profiles, supporting more efficient investigation and greater trust in the model's decisions. In terms of overall conclusions, our results highlight the importance of a data-centric approach. Removing duplicate records prevent inflated metrics. Scaling ensures fair learning, and applying SMART only on the transit enabled the model to learn fraud patterns under extreme class imbalance. Without SMART, the model would largely predict non-fraud. Fraud detection involves a trade-off between recall and precision. Our tuned random forest achieved a balanced performance with approximately 81% precision, 76% recall, and a ROC-AUC of 0.97, making it suitable for practical deployment. Although a natural network was also evaluated, the random forest was selected as the final model due to its stronger performance and interpretability. Future improvements may include cost-sensitive learning of additional feature engineering to further refine this balance. Thank you. That's overall.